I'm now planning to discuss with you about sensor physics. How can we make use of the physical phenomenon in order to measure a physical property and create a sensor that can give an electrical signal on the output that is proportional to this physical property. And different kinds of sensor techniques, how to connect the sensor to make a useful electrical signal out of it. An electrical signal that can be connected to a measurement system for further processing. The outline of my presentation today will be about basic sensor physics first of all, and different kinds of physical properties and how they can be measured. Resistors, thermocouple elements for measuring temperature, NTC resistor for measuring temperatures, strain gauge, piezo crystal, differential transformer, Hall sensor, photodiode, and then we come to the sensing techniques using bridge connected sensors, using the 4-point method, and using a relaxation oscillator. So if we have a sensor, as in this case we would like to measure the temperature inside this toaster, how can we create a sensor and make use of a physical property such that the temperature can be converted into a scalar value that can be carried by the electrical output signal from this sensor? That is the question, main question in the first part of my presentation, and related to different kinds of physical properties, not only temperature, of course. All kinds of resistors has some dependency with temperature. And let's say that we want to include this resistor into a circuit board for some kind of electronic design, then I think this dependency with temperature is not very desired. So we choose a material in this resistor that has the lowest possible dependency with temperature. But on the other hand, if we want to use it as a sensor, then we want to maximize the material dependency towards temperature. So have a look at this diagram where the material is chosen to be the metal platinum. And you can see here the temperature dependency from -200 degrees to 1000 degrees Celsius. And the corresponding difference is between somewhere to 0 to almost like 500 ohms. And the dependency is pretty much linear. And this is a thin wire, metal wire, where you can adjust the length and the cross area of this wire such that the resistance at 0 degrees can correspond to 100 ohms. This is what they have been doing here in this graphical presentation. And they describe the temperature dependency with the coefficient gamma. And then you can of course get different kinds of temperature dependencies depending on what kind of material you choose for your resistor. So it could be for platinum, it could be for nickel, and it could be the corresponding for copper, where we can see here that nickel seems to have the highest dependency towards temperature. A German scientist, Seebeck, discovered that an electrical conductor that is exposed to a temperature gradient from one end to the other end is generating an EMF, a voltage that is basically proportional to the temperature difference. And a number of different materials has been quantified because this generated voltage is dependent on the actual material. Material has been quantified with a constant, this thermocouple constant beta, and which quantifies the material in relation to the metal platinum. And the thermocouple constant for the metal platinum has been defined as being equal to 0. What we see here is an arrangement for measuring the temperature difference between two solder points T2 and T1. And the idea here is that the voltage that is going to be read here on this meter, voltage meter, is going to be proportional to the temperature difference. And in this case we have been using two materials, material A and material B, from the points T2 to T1. And we have been using the same material in the wires that are connected from point T1, electrical wires that are connected to the voltage meter. So the same material C for the wires that are connected to the voltage meter. And we can also denote the temperature as T0 at the point where we have the voltage meter. The voltage is denoted by V, that is red. And the whole idea here is that we should now be able to show that the material C will be eliminated from the temperature reading. And I'm going to show you how we can develop an equation, an expression for the voltage that we can read over the meter. And we will develop it from the first voltage, Kirchhoff's voltage law. I have made a notation of the voltage generated over material A as EA, and from temperature T2 to T1. And the idea is that we should make a potential travel from this point over this closed circuit and come back to the same point, and then the sum of all the potential differences should be equal to 0 according to Kirchhoff's voltage law. So we start here from T2 to T1, which is the voltage generated over material A, and then continue with material C from temperature T1 to T0, minus the voltage that we read over the meter, plus the voltage generated again over material C, but on the second wire from T0 to T1, plus the voltage generated over material B from temperature T1 to T2. And the sum of all of these potential differences should be equal to 0. Now, if you look at the potential difference over material C from T1 to T0, I think we can agree that this should be equal to minus the potential difference over the minus the voltage over material C from T0 to T1, which we have actually on the other wire. So it means that the voltage generator over material C on this wire and on this wire will eliminate each other, and we can eliminate this term from this term, because you can exchange this one with EC, the voltage over material C, minus this one from T1 to T0. And we can further develop this equation to solve for the voltage V, which we are interested in, which will be the potential over material A from T2 to T1 minus the potential over difference over material B from T2 to T1. And then this we can denote as the combination of the materials A and B. So the potential difference of the combination of the materials A and B from temperature T2 to T1 will approximately be equal to the coefficient beta, this material coefficient, from temperature T2 to T minus T1. And we can have different kinds of material coefficient depending on the pair of material that we are using. Iron versus copper nickel. Copper nickel then is an alloy, and it is classified as the type J of temperature sensor. We have the alloy nickel chromium in combination with nickel aluminum, platinum and 10% platinum, and then rhodium, which is also an alloy in combination with platinum. And they are made for different temperature sensing intervals. So within this kind of interval, the sensor is reasonably linear. But you see that they are not completely perfectly linear. So I know that I have seen some of the suppliers of these thermocouple elements, they can also provide you with data of a higher order polynomial, not only one single coefficient, to describe a complete polynomial, to have a description, have as a description of the temperature dependency. Well, I'm going to show you just a little bit more of the same, actually. This is just another kind of circuit, and it's connected a little bit like differently. So you see here that we are now going to measure the temperature difference between these 2 points, T2 and T1, and we will show how the connection point to the wires that goes to the instrument, the meter, is eliminated, and also the material in those wires, by again using the Kirchhoff's voltage law. So we start from this point using material A from temperature T2 to T1, corresponds to this part, and then plus material B from T1 to T3, corresponds to this part of the wire. Yeah. And then we have this EC, material C, from T3 to Tm. Tm is at the point where we measure the voltage. This will be this part of the wire. And minus the voltage over the meter, and plus the voltage generated over material C, this part, from temperature Tm to T3 again, this one, and plus the voltage generated over material B from T3 to T2, and all of these potential differences should be equal to 0. And we can conclude that this EC, T3 to Tm, which is on material C, that should be equal to minus EC Tm to T3, which will make these two elements to be eliminated, these two terms. And if you look at these two terms, the blue ones here, the voltage EB from T1 to T3 plus the voltage EB from T3 to T2, I mean, that should be basically equal to the voltage from over material EB from T1 to T2. So we can eliminate the point of T3. This can be seen on the next line. So voltage V is solved for, which is the voltage over material A, T2 to T1, corresponding to this point, plus voltage over material B from T1 to T2, according to what I said about these two blue terms, which is approximately equal to this material coefficient for the material combination of AB multiplied with T1 minus T2. A semiconductor material can be doped to have a certain resistance, and this semiconductor material could be actually a small area that can be integrated directly on any kind of CMOS circuit, integrated chip. But then the drawback is that this temperature sensor will be very much unlinear, have an unlinear response. If you look at this diagram here, you see the temperature on the horizontal axis, and you see the resistance on the vertical axis, and there is a negative temperature coefficient in this case. So the temperature, with increasing temperature, the resistance is decreasing, and it is decreasing with a logarithmic response following this definition, this equation. This factor R infinite is defined by this equation, and this T is the temperature, capital T is the temperature given in Kelvin, and alpha is the exponential coefficient. And for the computation of R infinite, then R0 is the resistance at any kind of chosen temperature T0. In this case, R infinite has been computed at the temperature at 298 Kelvin, being 1 kilo ohms, resulting in an alpha of 3000 Kelvin. This is a very low cost sensor, and it can be, as I said, integrated on a chip. However, it is far from being linear. But I'm now going to show you how we can add linearization network in order to improve the linearity of this kind of sensor. Indeed, it is as simple as combining this NTC resistor with another resistor into a voltage divider, where the other linearization resistor has a negligible temperature dependency. Have a look at this circuit diagram, where you see a typical voltage divider. And this is the linearization resistor that we are adding, and we get the corresponding expression for the output voltage UR, having a constant input voltage U. And we can separate this expression into U and N lin for this linearization network. And you know that the NTC resistor had decreasing resistance for increasing temperature, but the linearization network has increasing value for increasing temperature. So I think one can realize that these two relations could somehow compensate for each other. So let's satisfy with that kind of intuitive conclusion for now, and then we will continue to analyze this linearization network. The question is then, of course, how to select the best value for this linearization resistor in order to achieve this. For this, I suggest that we select 2 or 3 temperature points that are equally spaced, such that you have TA and TC, and then TB should be somewhere, should be exactly in the middle, with the same distance to TC as for TA. Can be expressed this way mathematically. And then we can kind of express an equation for a straight line, because we want to have this linear dependency that is expressed by a straight line. And we can say that the voltage spacing equally UR between point A and B should be equal to as between point C and point B. This is expressed in this equation for this straight line. And then if we combine this expression with the previous expression for this UR, then we can solve for the R linearization resistance. U will be eliminated along the way. I have not developed the whole, made the whole development, but you can do this as an exercise yourself. Anyway, this is the final expression that I achieved. We can continue with this on the next slide. You can see these 3 points A, B, C on the curve of this NTC resistor that we want to linearize. You have the temperatures 273, 298 and 323 Kelvin, and you have the corresponding resistance values here in this table. And I have shown that the space in between TB-TA and TC-TB are equal to 25 Kelvin. And I was able to use the equation from previous slide and compute the linearization resistance to be optimal at 682 ohms. But then we should maybe analyze and see how will the corresponding output voltage UR look like now when we added this linearization resistor. How will the temperature dependency look like? We can look at the next slide. We see here the 3 different points on this NTC resistor, and you can see here how the linearization network look like. And with the computer resistance value, you will get this kind of response between 270 and 330 Kelvin. And now it looks pretty much like a line here in this range. So it seems like this linearization actually works. A conductor, when it is exposed to mechanical stress, compression, or if it is like pulling this electrical conductor, its relation between the length and the cross-section area will change, and that way also the resistance in this wire will change. If you use this phenomenon and this physical property and you glue this kind of wire onto another object, then it is possible to measure the amount of force that this object is exposed to. You can have a look at this sketch here where they have this thin wire, an electrical conductor of the length of L and the cross-section area of A. And this material, depending on what kind of material used, you have its resistivity of ρ. And the resistance of this conductor will also then be proportional to the quote between the length and the area. And when you add some kind of force, pulling force in this case, to this wire, then the length will increase, and at the same time also the cross-section area will decrease, because you have, of course, always the same amount of the same volume of material, and that will change this quote of length divided by area, and the resistance of this conductor will then change. And we can use this property to actually measure the amount of force that is exposed to some kind of object. Here you see a strain gauge sensor where you have this conductor that is printed on this substrate in a number of loops to increase its sensitivity, and it will have a principal sensing axis then in this direction, because when you're exposing the strain gauge detector sensor of force in this direction, then the length and cross-section area of these wires will all change. And then the idea is that you can use this sensor, and you take this substrate and you glue it onto another kind of object. If it is a rod, then mechanical rod, some metal rod, you can actually measure the weight of an object. Or you could possibly also assemble this strain gauge sensor on a shaft, and then you could measure the torque U on that shaft using this strain gauge sensor. If we expose a piezoelectric crystal with a force, external force, there will be a change of the charges inside the crystal material such that we are able to measure a voltage on its surfaces. Have a look at this drawing where you see the internal crystal structure, and there is a force that is compressing the material in such a way that you can view it as an accumulation of negative charges on one surface and positive charges on another surface, allowing us to actually measure a voltage over this piezoelectric crystal as if it was a charged capacitor. We model this crystal as an equivalent electrical circuit having a current generator that is generating current then when it is exposed to forces. a capacitor and a resistor. The resistor here is used because the charge will not be maintained for infinite amount of time. So after a while it will start to disappear, even if we have an applied force. And we can start to develop equations for this. We can say that the force, actually the generated amount of charges is proportional to a sensor constant K multiplied with the force Fx. And we can say that the current then is dq dt. That is a known definition. And it is equal then to K times df dt. And the voltage over that capacitor that we see here, that one is the charge Qx divided by its capacitance Cx. But since, as I mentioned before, the crystal also has a resistance, or it is like losing its charges after some time, then we are model this system as a first order differential equation with a decharging resistor of this capacitor according to this equation that we see here. And these kind of sensors can be used in different kind of applications for measuring forces. There are situations, could be in automation, when you want to measure the position of a valve as it is closing or opening. This is just an example. And one way to measure the position of the valve could be to use a differential transformer. Have a look at this principal sketch. And the output of the differential transformer will be dependent on where this kernel is positioned. And by changing the kernel, you can actually also change, measure the position of the object that is changing this kernel. On the upper side we see the waveforms. The blue waveform is the input and the green one is the output. And when the kernel is approaching the upper secondary winding, then there is no phase shift. But when the kernel is approaching the downside secondary winding, there will be like a 180 degrees phase shift. And the closer to the end, the more this winding will contribute to the output voltage, and the more to this side, the more this will secondary winding will contribute to the output. And we will have an output voltage that is more or less linear, proportional to the position of the kernel. A Hall effect sensor is used to measure the strength of a magnetic field. And it is doing so by using the fact that a charged particle that enters into this magnetic field is bending its motional path due to the force it is exposed to. You can have a look at this principal sketch that I have prepared, and you see a charged particle, an electron, that is moving in this direction. And if you have the negative charge in this direction, it means that the current is actually flowing in the other direction, the current dq dt. And where there is a flow of current of charges, there is also a magnetic field surrounding this flow. And the direction of this magnetic field you can determine by the rule of thumb that you most likely have learned in your physics courses, which tell me that the field vector then will go into the presentation at this point and will come out of the presentation at this point. And then the charged particles and the flow of current enters into the area where you have this magnetic field, homogeneous field, where the field vectors are everywhere entering into the presentation. And then there will be a force onto this charge that will try to move or will expose the charge in this direction and bend its motional path in this direction. And this is also known that then as this Lorentz force that can be expressed according to this formula. Q is the charge of the particle E is possibly a field vector, but then in this case, in this illustration, this electrical field vector is 0. But we have a magnetic field vector B, and the charge also has a motion vector V. The actual Hall effect sensor is basically a semiconductor material, and we are driving a current through this semiconductor material by using an external current source. And then this material is exposed to the magnetic fields, and when the motions of the charges that is traveling through the material is bending towards one direction, then it means that you will have an accumulation of charges on one side, positive charges and negative charges on the other side. And this difference in potential can be measured by a voltage meter from the outside if you add this detecting connection here. The generated Hall voltage will be proportional to the current that is flowing through the semiconductor material, and proportional to the magnetic field strength, and reversely proportional to the thickness of this material. If you keep the current and the thickness of the material constant in combination with this Hall coefficient, the Hall coefficient is material dependent. If you keep this part constant, then you can have an output voltage that is proportional to the magnetic field B, and with a sensor coefficient that is expressed by this part, the Hall coefficient times the current and divided by the thickness of the material. So this is a detector that can also measure a constant magnetic field, not only a changing magnetic field as we can do with a simple coil. A photodiode is used to measure the light intensity from any kind of source. And this diode is basically the same kind of diode as any other kind of diodes that are used in electronic circuitry, except that they made the junction visible, the junction between the N-doped and the P-doped material in the diode, to allow light energy to generate current in the diode. It can also be compared with solar panels used to harvest electrical energy from light directly. Have a look at this principal sketch of a photodiode made of semiconductor material that are N-doped and P-doped, and due to the excessive negative charges on one side and positive charges on the other side, it will create a diffusion current, a flow of diffusion into the area, and this will create a depletion area that is ionized, and due to ionization then we will also get an electrical field vector, and this depletion area will then be free of any kind of free, it will completely empty of free charges that can carry a current. But what happens when a photon is entering this area from the outside is that the energy from this photon is generating a pair of electron and hole. And this pair of electron and hole will then follow the electrical field vector inside this junction and create a net current that is flowing through the photodiode and this closed circuit. And this net current can then be measured by an external measurement system, and it will be in relation to the amount of light that is entering this area. We see here the diagram for the voltage current characteristics for the diode, voltage on the horizontal axis and current on the vertical axis, and you can see that the curve is then shifted if there is light coming from the outside. A resistive sensor is a passive sensor that generates voltage on the output that is ideally proportional to the change of the physical property. And if the sensor coefficient is very small, such that the resistance changes are small, then a bridge is used to increase its sensitivity. And this quarter bridge is a kind of an electrical interface to convert the property of resistance into the property of voltage, which carries the output signal, the electrical output signal, further connected to the measurement system. What we see here is the resistive sensor, how it is connected in combination with 3 other resistors into something that is called a quarter bridge. It is called a quarter bridge because just 1 out of 4 are used as the resistive sensor, and the rest of the resistors have fixed values. Now, if we assume that at the reference level of that resistive sensor, the resistance value that the sensor has at the reference level, if we assign that resistance value to the rest of the 3 resistors with a fixed value, then we have a bridge in balance at reference level, and R1 divided by R2 and R4 divided by R3 is equal to UA minus UB equal to 0, and there is a 0 output. And any change of the resistance value of this resistive sensor, dR, will then generate a voltage on the output terminal UAV. And very often these bridges are supplied together, built into the resistive sensor, as close as ever possible to the sensor itself. And in those cases, the sensor has 4 terminals, not only 2 terminals, but 4. It is possible to further increase the sensitivity by using half bridge and full bridge. Half bridge means that 2 of the 4 sensors have a resistive sensor, and it's made in such a way that the response to the change of the physical property must be in the negative order on one of the resistors and in positive order on the other resistor. In full bridge, then all of the 4 resistors are sensitive to change of the physical property. That will of course then generate the highest possible sensitivity. I think it's reasonable to believe that the temperature dependency of the resistive sensor will be equal for both that are connected in a bridge, and thus the contribution of resistance will be equal on both sensors, which allow us to also suppress the temperature dependency for that specific resistive sensor. The same goes also for the full bridge. So whenever you have more than one resistive sensor connected into the bridge. It is possible also, of course, to use a bridge for measuring an inductive sensor. This is the inductive sensor in this case, and the inductance that this inductive sensor has at the reference level is also assigned to the corresponding inductance forming a pair. So G omega L and G omega L for both of them at the reference level. So if the inductance is at the reference level for the inductive sensor, then the output will be equal to 0. And we can form the corresponding expression for the output voltage as UAB, UA minus UB, and this expression here is based on the voltage division through these reactances, and it is of course then assumed that there is no kind of magnetic coupling between those 2 inductances. and the voltage on VUB on this node is assumed to be half the voltage U, assuming that R4 and R3 are equal to R. And we can make an expression also for the sensitivity of the bridge according to this formula. The simplest form of using a resistive sensor could of course be to only have like a constant current generator and just measure the voltage over the resistive sensor. And that can sometimes be used also, but if so, then you still need to consider if to use the two-point method or the 4-point method. And I'm now going to explain to you what is the difference and the advantages with the 4-point method. So if you look at this simple principle sketch of a resistive sensor, and you have this constant current generator, and you have the meter where you actually measure the voltage that is generated over the resistive sensor. Then we are driving the current through one pair of wires, the constant current, and that constant current will of course be adjusted even if the resistance in any way changes in the resistive sensor or in the wires. There could of course be a temperature dependency of the resistance, the long path of wire, if it is drawn wires on a long distance to connect between the constant current generator and the resistive sensor. So in order to avoid the contribution of the voltage drop that comes from this resistance in the wires, we use completely separate wire to measure the voltage directly over the resistive sensor. And the benefit is then that there is no current that is actually flowing through these wires, since the voltage meter is a high impedance voltage meter. The other way would be then to use a two-point method and connect the voltage meter directly to the wires here close to the constant current generator. But then if there are any kind of temperature dependency on the wires that could have a large resistance if connected on a far away distance, then this one also will erroneously contribute to the measured values and not only responding to the physical properties that is related to the resistive sensor. So this is the benefit with using the 4-point method, that there is no current flowing through the wires that are connected to the voltage meter. This slide is showing the final method for interfacing sensors and connecting to them between the sensor and the measurement system. And it's a relaxation oscillator. It's an oscillator that is based on an operational amplifier, and its output will be a square wave oscillating frequency, and the frequency of this oscillator will be dependent on the two components, the measuring capacitance or the measuring resistance. And if you keep the resistance constant, and then the output will be reversely proportional to the capacitance, or if you keep the capacitance constant, then the output frequency will be reversely proportional to the resistive sensor. Yeah, this could be a good way and a way of transferring the measurement value over large distance, and that is also quite insensitive to noise disturbance.